All right, so today we're going to continue we previewed loops last time, and today we're going to start it formally. Remember that loops basically have four parts to them. Just like if you're a loop, the reason that you'd want to write a loop is that you're doing some piece of code over and over and over again. And so of course you need four components. You need a starting point. You need to know if you should continue the loop or not. And then of course you need to make progress towards that termination condition that says, no, you shouldn't do that loop anymore. Because if you don't, then you're caught in this infinite loop. And of course, you actually do something in your loop. Let me make sure. Yeah, you actually do something in your loop, and so that's the loop body. So for example, we started out with the for loop and the while loop here with very, very simple syntax. All it's doing is counting to 10. Right? We have an initialization here where we've got what this is called an index variable. We started at 1. And while I is less than or equal to 10, we continue executing whatever is in this loop body. And in this case, we're just printing it out. And then we increment I by 1. This is new syntax that we'll talk about in detail here in a moment. Yeah, go ahead.
Do you have to declare, like, the variable I before you write a for loop, or is I just, like, in the loop always?
Good question. We'll get to a small distinction to scoping later on. This is the preferred way, though.
You don't have to, like, declare I before the
With the while loop, you definitely do. Yep. But the for loop, you can declare it, and when you declare it like this, the scope is limited to that loop only.
Okay.
The variable only exists for that loop, not after that loop, not before that loop.
Okay.
Right? Okay. So to get an idea of what this looks like, I've pulled up this visualization tool here. The website is called pythontutor.com, but it supports multiple languages. And I just stuck in that basic for loop there. And what we're going to do is we're going to step through this program. Now, this is not a real development environment. It's not a real debugger. It is just a way to visualize code and step through to see how it works. So what we're going to do is we're going to step through this and look and see how the variable I changes on each iteration of this loop. One time through the loop is called an iteration. The first iteration, the second iteration, ... the last iteration. So when I go ahead and enter this loop, we'll see over here that I has a value of 1. We then go to line 4 and we actually print it out. So the printout over here says 1. We then go back up to the top of the loop, and this I++ will now execute, and we'll see the variable I here change to 2. Right? It's just counting. And then it prints out 2, and likewise it goes back up to the top of the loop, executes that increment statement, going to the next value, I++, 4, 5, 6, 7, 8, 9. It prints out 9. It comes back up to the top, and I then increments to 10. Right? So now, is 10 less than or equal to 10? Yes, the way that we've written it. So it'll execute one more time, and it comes back up to the last, that was the last iteration, but it does come back up to the top of the loop, and increments I to 11. We didn't see that because it goes out of scope, but now it's 11. Is 11 less than or equal to 10? No, so it's done executing. Okay? Let's see the same thing here, but within the context of a while loop. Right? So it doesn't have to look pretty. I'm just going to go ahead and cut and paste it and visualize the execution here. Now, we've declared I outside the loop here, and so it gets initialized on line 3, and we see 1 here. Then while I is less than or equal to 10, so 1 is less than or equal to 10, so this entire loop body executes. We print it out, and then at the end of the loop, we increment I++ to the next value 2. Right? So same exact behavior as before. It goes over and over and over again while this condition in the while loop here is true. With the for loop, the condition was right here. While that condition in either loop is true, it will execute at least one more time. Okay? Keep going until we get to, say, 9. Right? Now, 9 is less than or equal to 10, so it will execute one more time, increments to 10. 10 is less than or equal to 10, so it executes one more time, and this is the last time. It prints 10, increments to 11. Right? Now, here we actually did see it go up to 11 because we declared it outside the loop, as you already observed. So it does come back up here to the while loop and makes the check. Is 11 less than or equal to 10? Nope. So what happens? it goes to the end, right? Jumps out of the loop and then continues with whatever. If you have more code after that, then it starts executing that code, right? There's that visualization of these two. Now let's talk about each one of these in detail, right? Okay. All right, remember that we are online, so if you have any questions, you can go ahead and post to Piazza or to YouTube, the YouTube chat. All right, so let's talk about for loops in detail now. Right. The three main parts, that is the parts initialization, continuation, and increment, are all on the same line, right? As we see up here. There we go. Here's the initialization. Here's the continuation condition. While that's true, go ahead and execute this one more time. And then the increment here is the third statement. Okay. The loop will continue to execute as long as the continuation condition evaluates to true. The second that it evaluates to false, when it evaluates to false, this is the termination condition. The loop ends and normal control flow continues after. So if you've got more code after that loop, then it starts executing normally A, B, C, D, E, F, G, right? So let's take a look at the syntax, right? So what can you observe about the syntax up here? Well, first of all, you use this keyword what? For. That's why we call it a for loop. Second, you see a semicolon on the initialization statement, a semicolon on the continuation statement, and do you see a semicolon on the increment statement? No. Weird, inconsistent, I would agree, but that's what it is, right? So we use the keyword for, right? Semicolons, and the initialization and continuation, but not the increment statement. Okay. The body is surrounded by, like all code blocks, what was it surrounded by? An opening curly bracket and a closing curly bracket. Style-wise, what did we do inside the loop body? Right? It's surrounded by curly brackets, and its contents are, what did I do to it? I indented them. Indented one level. Right. There we go. All right. Looks like we're dropping a few frames, so hopefully that's not that doesn't cause a huge issue. But so what? All right. All right. So, as you already observed, this declaration means that I am for the for loop, that is. That this creation of we call this an index variable, by declaring it inside the for loop, then we limit the scope of that variable. Okay, so declaring the index variable inside the for loop scopes it to that loop only. Right? So what does scoping mean? Think about a scope in real life, right? When you look through a scope, can you see the entire world? No, you can only see what's in the scope, right? It is limiting your vision. It limits where a variable lives and can exist and can be used, right? So the scope of a variable is the segment of code in which it lives or is valid. Right? So by limiting the scope to that for loop, by limiting it, the index variable only exists in the for loop, not before nor after. So let's take a look at an example here with a full development environment here. Right? So here's my printf I is equal to %d and the line I. Now, what would happen if I tried to print it before? That should be pretty straightforward. Can you use a variable before you've declared it in C? No. So this should be really easy to tell that this is going to be a compiler error, right? GCC demo.c. I don't know why it's not looking all that great, but so be it. It's telling me that there's an error on line 9, and I is undeclared. Okay, so that's pretty clear. But what about after? Certainly I've declared it on line 9, but because I've scoped it to that loop only, it only exists for line 9 through line 11. After that, it no longer exists. This will also be a compiler error because it says that I only exists for that loop. After that loop, it no longer exists. Okay? This is a very good thing. In general, it is best to limit the scope of all variables as much as possible, because you want your code to be simple, right? You don't want to worry about too many what are called side effects. You want to limit the scope of variables so that you don't have 50 variable, you don't have your variable shouldn't live beyond what is necessary for it to live, right? You could go to the other extreme. You could create all global variables being outside of main, right? For example, and don't do this because it's very bad. In fact, we say globals are evil. Int I. Right? I've got like 54 loops in my program. I'll just go ahead and declare it out over here, and it exists. It exists everywhere in your code now, right? Any attempt to recreate an I here will be either a compiler error or it'll be a different scope, right? In any case, don't do that. Globals are evil, right? You want to limit the scope of variables as much as possible, right? Only limit them to where you need them. Only use that which you need, right? Okay, so observations. Right? We have new syntax here. I++ adds 1 to the variable I. So in general, you can do this with any numerical value, but it really only makes sense in the context of integers, right? 3.14159 plus plus, yeah, that'll go to 4.14159, but don't do that, right? It's weird, and it's intended only for integers. Likewise, we also have, this is called the increment operator. Right? It's equivalent, and I'll put that in quotes there, to saying that I is equal to I plus 1. Right? And I say that it's equivalent because it's actually not equivalent. It has the same effect. It adds 1 to the variable I, but in this first instance, there is one variable and one operand. In the second instance here, there are 2 operands. There's a plus operator, and then there's an assignment operator. Right? So having 1 operand versus 2 operands, they're not the same thing. And all 3 of these have different orders of precedence. Just like PEMDAS, right? You do addition and subtraction before, or you do multiplication and division before addition and subtraction, right? For the life of me, I don't remember which one is which, right? I don't know which one has the highest order of precedence, which one has the lowest order of precedence. I don't want to have to worry about those things. So I write nice, clean code with no ambiguities, so I don't have to go back and research and what was the order of precedence operators again, right? Don't worry about it. Write nice, clean code, and you won't have to memorize that kind of garbage. Okay? I don't, right? So it's equivalent to that, i.e., it has the same effect, but it is not actually equivalent to it. So we can go up by 1. You might be asking yourself, can you go down by 1? No. You can also use the decrement operator. And what do you think that looks like? I minus minus, exactly, right? You can also use compound assignment operators to add, subtract, multiply, divide by a constant or expression, but we won't do that. For example, you can go I equals I plus 5 can be rewritten as I plus equals 5. Right? Yeah, I'll go ahead and put a semicolon on the end of these because they are statements. Right? So it's just a shorthand, right? I is equal to I plus 5. That's saying add 5 to I. So by going plus equals, you can shorthand that and get away with just a few fewer characters, right? Why would you want to do something like this? Less typing, right? And if there's fewer things to read, guess what? Well, if there's fewer things to write, then there are fewer things to read. So once you get into the habit and once you understand and have seen these kind of operators, then code becomes more readable quicker, right? You can become a speed reader of code rather than a slow reader of code, right? You can also do that with the minus minus operator, right? With other values. I is equal to I minus 10, right? Can be rewritten. What do you think? I minus equals 10, right? You can also use multiplication. So I is equal to I times 2 can be rewritten as I times equals 2. Well, now what is that going to do with multiplication? If I was 10 before, multiplying by 2 is going to give me 20, and so 20 will now be an I after this. Okay? You can also do division, but be careful. Division 2, but I divided by equals 2, right? i.e. integer truncation is possible. Right? 10 divided by 2, that is going to give me 5. That makes sense. But 9 divided by 2 is going to give me what? 4.5, then truncation, throw it out, I get 4. Right?
We did divided by equals and what is it, cast it to double?
You could do maybe something like this, but implicitly here I is already an integer,
Yeah.
so you're not going to be able to store 4.5 no matter what you do into I. Right? Okay. So those are compound assignment operators. And you can use them not just with for loops, but you can use them anywhere in your code now that we've seen them. Okay? It provides a shorthand way of doing things, an abbreviation. Again, it all goes back to syntactic sugar, right? You don't need sugar, but you want sugar. Why? Because it makes the language more flexible. It makes it easier to use. It makes it easier to read and write in that language. Right? You don't need 50 different adjectives to say good. In English, you could just have good, right? But then that wouldn't be a very rich language. Right? All right. What about while loops? And again, here, so that I don't have to keep scrolling up, let me go ahead and bring this code down here as well so that we can see it again. And now, where is the initialization condition here? Initialization statement is before the loop. Right? Then you don't have a well-defined starting point. If I didn't even declare I, like I did right here, there's no way that I could compare it to another variable. If I didn't set it equal to 1, in other words, I had this code right here. Right? What value is an I after that first line? Who knows? Right? 99 times out of 100, it will be 0 and not 1 like I wanted. So you'd count up 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's not even what I want. But you know, in that one time out of 100, there could be garbage values. There could be dead beef values, flag values to indicate uninitialized memory. Some random value. Right? So make sure that you're always initializing your variables properly. The initialization statement is before the loop. The continuation statement is tied to the while keyword. Right? The body, right, is again surrounded by parentheses, by curly brackets. Right? And the increment is done typically at the end of the loop. But here's the main difference with a while loop. You have more control on when it happens. It doesn't have to be at the end of that while loop there. So what I mean by that is, let's go ahead and bring this code over to our coding environment. And we'll clean it up here. A style on demo. There we go. Now, nice and clean. Right? Most people have had good, we're grading Hack 2 right now, and most people seem to have good style. It's okay to use a tool like A-style, but you really should be getting into the habit of writing nice, clean code up front. Right? Don't get into the habit of writing garbage code and then just worrying about a tool later on. When you write garbage code that doesn't look very good, it is not readable for yourself or others, right? And you get into that bad habit, and that bad habit stays with you. Bad habits are very, very tough to break. Good habits are very, very easy to break, right? All right, so let's go ahead and compile this demo and run it. And you see 1, 2, 3, 4, 5, 6, print it. What if I increment it before I print it? This is perfectly fine, syntactically correct. Come on. There we go. But what will it print now? It'll go to 11, right? Where will it start, though? 2. 2. Why 2? 1 is less than or equal to 10, but immediately, what do I do the first thing in the body? Increment it to 2. So it starts at 2 and goes all the way to 11. Why did it go all the way to the 11? Because it comes in at 10. 10 is less than or equal to 11, 10, but then it goes up to 11, and I've run out of fingers, but then it prints out 11. Right? Only when it goes back up to the top of the loop, sees that it is now 11, does it break out of the loop and go on, keep going. Yeah?
So if you were to print out like I, like after the loop was over, like after the curly brackets, would it be 10 or 11, or would it be back to 1, like what it started with?
Good question. Make a prediction here. I is now equal to this. So how did I break out of this loop? I is no longer less than or equal to 10. In other words, it is 11. It got printed that way. It comes back up, says 11 is not less than or equal to 10, and then it continues on. But because I declared it before the loop, it exists in this entire function. That's its scope, right? It's like having a small scope and looking at a small area, microscope, and then having a macroscope, or telescope. Right? I've increased the scope of that thing, right? And it will actually print out that it is now 11. Right? That's not. That's a consequence of using a while loop. You're not able to have the same control like we did with a for loop and limit the scope to that loop only. You can't do something like this. Right? Well, here I'll try. Right? While I int I equals 1, I is this, right? That's not going to compile. That's not correct syntax. If you want something like that, you're shopping at the for loop store, right? Get out of the while loop store and go to the for loop store. Right?
Can you increment using something other than 1?
Yes, that's what the compound assignment operators can do.
I'm sorry,
Right.
for a for loop?
Yes, we'll do some more practice later on, but for int I, we'll start it at 10. I is less than or equal to 100. I plus equals 10. And this will go 10, 20, 30, 40, 50, all the way up to 100.
Can you do something more complex than that?
How complex do you want to be?
I don't know. I'm trying to put it.
Negative b plus minus, or plus square root of,
Oh, there you go.
yep, b squared minus 4 times a times c. Yeah, you can put any expression there whatsoever. This is just like putting this out into a regular statement, right? Whatever you can put into a regular statement, you can put here. The only difference being that you do not have a semicolon at the end of this. In fact, you can get real fancy if you really want to. Not that you should. In fact, I hesitate to even show this to you. Printf, hello, and the line. What's that going to do? Infinite loop of hello, 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 hello. Right? Why? There is an increment statement. There is a continuation statement. There is an increment statement. It's just that they're all empty. Do nothing. While nothing. Do nothing. Right? And then print.
Would it do the same thing if your increment was I equals 0?
Yes. Yep. Then if you printed it out, it would be 0, 0, 0, 0, 0, 0, 0. So we're caught in an infinite loop here. How do we stop it? How do we get off this train? Refresh the whole page. Definitely don't want to do that. That's a waste of time. What I just did was Control C, and that will work on Windows as well. Right? That kills whatever the current process is running. Okay. And if you want to, you can go ahead and clear out the the terminal here. Right? You can open multiple terminals here in this VS Code version, and you can also do the same in the CS50 IDE. If you want to run multiple processes in parallel, that goes a little bit far, though. Okay? All right. So, again, with another difference is that you cannot scope an index variable to be limited to the while loop, right? Unlike a for loop, okay? All right, let's see. So, I showed you two loops. Why do you want to use one versus the other? For loop versus while loop. You might be asking yourself, do I have to write a for loop? Do I have to write a while loop? The answer is you don't need both, all right? Any for loop can be rewritten as an equivalent while loop and vice versa. Right? You can take a while loop and rewrite it as an equivalent for loop. All you need to do is take those three components and be careful about where you put them, all right? While loop to a for loop, you have to make sure that your increment was done at the end of the loop. Right? There are also do while loops that we're not going to cover, but if you want to, you can go ahead and check those out. In the reading, we talk about them. But why do we want two for loops? Same reason that we want compound assignment operators. We want our language, and we want 50 different adjectives to mean good, right? We want a richer language. We want a more flexible language. Sometimes it's more natural to use a for loop, and other times it's more natural to use a while loop, right? It is generally natural to use a for loop when you know upfront, or if you've ever heard this term, a priori, right? How many iterations you will execute. Right? For example, I know that I want to count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? It's more natural to use a for loop in that case. When you don't know how many iterations that you're going to be doing up front, then it's more natural to use a while loop. Right? It is more natural to use a while loop when the number of iterations is not known up front. And the number of iterations could be a variable. For example, if I just wanted to write a for loop to count from 1 to n, where n is read in by the user, it's still more natural to use a for loop. But a while loop is more natural when you don't know that it depends on the input. How many iterations is this actually going to go? So to help you understand that a little bit, let's go ahead and give you an exercise here. Given a number, n, output how many digits are in it, ... So for example, if I have an int n, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9, first of all, is that too big for an integer? It's 123 million. Is that too big? Nope. What's too big? You learned that last week in lab. 2.147 billion, right? And change, that's the maximum value in an integer. So we're good to go here. What would I want to output in this case, though? How many digits are in that number? 9, right? If I said my input was 1, 2, 3, 4, well, I would want to output that it has 4 digits, right? So let's go ahead and go with that input right there, 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's write a loop to do this, right? So let's create a variable to count the number of digits, num digits, equals 0 to start out here. And I'll go through and I'll count. Well, there's 1 digit, there's another digit, there's another digit, there's another digit, until I get down to the end, and then I'll report that there are 9 digits in this particular case. I want to write a loop to do that. Ideas. Okay, a while loop. While something. I'll do something. Is this big enough for everybody in the back? Right. Anybody who's streaming, let me know if it's big enough. I'm almost on 4K here, but whatever. Should be, at least the high def version, when it gets processed, it'll be clear enough. Right. So, while what? Oh, okay. Why do you want to divide it by 10? Take this number. In fact, let's make it smaller so that we can deal with it a little bit more in our easier in our brains. 1, 2, 3, 4, 1,234. If I divided that by 10, what would happen? It'd be 123.4, and if I did integer division, that 0.4 would be thrown away. Now I'm left with 1, 2, 3. Do that again. I'm left with 12. Again, when I divide 1 by 10, what do I get? 0, right? And that's where I'm done, right? I've counted up the number of digits. So let's go ahead and restore this now. 1, 2, 3, 4, 5, 6, 7, 8, 9. While n is greater than or equal to 0 or just greater than 0, I'm not sure. Right? We'll go ahead and leave it like this for now. Right? I will take n and divide it by 10. Understanding that 10 is an integer, n is an integer, so I'm doing integer truncation. That 0.9 gets thrown away. That 0.8 gets thrown away. Right? And each time I do this, I'm going to increment num digits by 1. Because when I divide by, when I shift it over, that's 1 digit. When I shift it over again, 2 digits, 3 digits, 4 digits, 5 digits, etc. Okay? And then I'll report it at the end. Printf. %d has %d digits, and the line. And then I will say that it's n and num digits. Except that I'm changing n, right? It's going to be, at the end here, it's going to be 0. And so when I print it out, it's going to be 0. So if I want to, I should keep track of the original variable. Original value equals n. And then I'll print out the original value rather than the modified n. Let's see if this works. Right. No syntax issues. So I would expect this to have an output of 9. Okay, back to the drawing board. Right. What was obviously wrong? It was just too intense of a calculation. I should be running it on my 2080 Ti or something, and then it'll get executed. No, we're stuck in an infinite loop here. Why? Yeah.
Because like when you divide 1 or whatever by 10,
It becomes 0.
0.
And now 0 is greater than or equal to 0, so it executes. But 0 divided by 10 is what? 0, right? So I probably want strictly greater than 0, because once I hit 0, I'm done, right? All right, let's try that again. There, and it's bad. Again, I don't know why it's crappy output there. Here, is this better? Nope. All right, but it does say it has 9 digits. Good. So, ship it. Is it done? Let's keep testing it. I should test something that is only 4 digits. Okay, that works, 4 digits. Hopefully you can squint and see that it is 4 digits. It looks way better up there than it does over here on this monitor. Maybe it's just the monitor. Okay, so anything else I should test? So negative values? Negative 120, there we go. How many digits does that have? Come on. Still 4, right? The negation doesn't count as a digit. And that still works. Right? Why? 1,000, here, let's kick it down to 12 here. Negative 12 divided by 10 is what? Negative 1. Negative 1 divided by 10 is negative 0.1, truncation, gets thrown away, gives you 0. It actually gives you technically negative 0, and there is such a thing as negative 0 in coding. Is there such a thing as negative 0 in math? Nope. But there is in code. Right? There is a negative 0.
How would it get into the while loop in the first place?
Good question. Does it?
I don't think so. I mean, obviously it did.
Yeah, I did compile it. I saved it, right? Negative 12 has 0 digits. There we go. Maybe I didn't save it. I screwed up. All right. So, yes, all is right with the world. Let's try that again on the larger number, 4, 5, 6, 7, 8, 9. There we go. Save. Actually, I think I did save it. It was that time when it was just not doing anything. It's being slow again. There we go. That's 0 digits. Is that correct? No. As you observed, we didn't ever get into that for loop. So, solutions?
Or less than 0. Yeah.
Or n is strictly less than 0. Okay. We can try that. 9 digits. All right. We need to do some regression testing now. Regression testing is where I tested this one thing before and it passed. I made a change so that I could fix this bug over here. But now that thing that passed before, did I break it? That's regression because it regresses. Right? Let's go ahead and try to see if that works by testing the original, and it is 9. Right? Is there a way that I could simplify this, though? Well, n is not equal to 0. Right? Right? Then continue. That's another way. What's another way mathematically? After I store off the original value, I could get rid of that negation. How? Abs or fabs? Abs because it's an integer. Right? And that'll work. Right? Say what?
Are you able to just put it in a while loop?
You could, but why would you do it over and over again when you only need to do it once? Right? Okay, that looks good. Any other optimization, not optimizations, but abbreviations? Remember here I did n is equal to n divided by 10. How could I shorthand that? Divide equals by 10. Num digits is equal to num digits plus 1. How could I shorthand that? Plus plus. Right. Make sure that everything still works. A dot out, 9 digits. Change, compile, test. Change, compile, test. Does that sound like a long-term good strategy? This is called ad hoc testing. I'm just throwing stuff at it until I have an assurance that it works. Good? Now, what I want is some way to automate this process. And that's where formal unit testing comes in. You'll get an exposure to that this Friday in your lab. We give you these unit tests that are designed to help you test your leap year function and your logic in your leap year function. Okay? But later on, we'll look at more formal unit testing frameworks like CMACA for C. Every language will have some sort of formal unit testing where you've got this unit of code and you want to test it. So you have inputs and expected outputs. And you run your inputs through your unit, and then it produces outputs. Does it match the expectation? If so, it passes. You write this in code so that it can automate all these 50, 100, 1,000 tests. So that you go in and you make one change, you make an optimization, or you change it to plus plus. You want to make sure that you didn't break anything. So you rerun all these 1,000 tests. If you're doing it in an ad hoc way like I'm doing right here, that's hours and hours and hours of manual labor. The whole reason we write programs and software is to avoid manual labor, right? And so writing more informal or formal unit tests is the way to go when you're testing stuff like this. All right. I think that that's good for now. So why did you tell me to use a while loop? Why did we do this entire exercise to begin with?
Because we didn't know how many times we would want to go through loops, so we used the while loop.
Right. Sometimes it was 4. Sometimes it was 10. Right. Sometimes it was 9. If we knew up front how many times this loop was going to execute, would we need to write the loop at all? Nope. If I told you up front, this while loop is going to execute 3 times, you have your answer right there. 3 digits. Right? All right. Is there one more test that I should try? Remember, in engineering, you've got corner cases, border cases, extremal cases. Right? Corner cases in mathematics. Write a function, 1 over x. Right? Is that defined everywhere? Where is it not defined? 0. What happens at 0? It blows up depending on if you're approaching from above or below. It blows down, right? So what happens at 0? It's undefined. What's going to happen here? How many digits does 0 have? 1. Right? 0 is a digit, right? It says 0 has 0 digits, right? So why does this happen? Take the absolute value of 0, it's still 0. Do we ever enter that while loop? Nope. So you might initially think, okay, well, I'll go ahead and throw this solution at it. We'll start the number of digits at 1. Is that going to work? That's going to screw up all my other calculations. 1, 2, 3, 4 is now going to have 5 digits. 1, 2, 3, 4, 5 is now going to have 6 digits. I'm off by 1. This is classic. How do you handle corner cases? How do you handle special cases, border cases, extremal cases? Ifs, right? So I'll say, you can put it up here, right? I don't know. Down here. If original value is equal to 0, then num digits is equal to 1. Right? Handle that case separately. That loop will never execute, so we don't care that that code is above there or not. Right? I could put that into an else statement, right? Else, and then I can move all of this stuff down here. Right? And then worry about indentation. I wonder if this works. Yep, it does. Highlight a block, tab, same results. Right? Again, you have to handle some special cases. Occasionally, you'll have to handle special cases separately. You have to do it in mathematics, right? If you say that you are at 1 over x at 0 is equal to NaN, right? If you were in math, though, what would you say? Undefined, hopefully, right? If you were in calc. But then calculus would say, okay, well, what if you take the limit of 1 over x as x approaches infinity from positive, or as it approaches 0 from above, plus? Then what's the limit? We all have calculus, right? I assume everybody's in engineering, so you've had at least one, or taking calculus currently. Yes? Right. It's separately. All right. I'll go ahead and put this in the notes so that you have it. But that's why we want to use a while loop sometimes. We don't know up front how many iterations we're going to go for. Whereas with a for loop, we do know how many iterations we're going to go for. Okay? You can also have nested loops. Nested loops. You can have a loop inside a loop. Right? We refer to them as the outer loop or the inner loop. You can also have a loop within a loop within a loop. Right? 3 nested loops. Inner or outer for loop, or outer loop, middle loop, and inner loop. The names get complicated because now you have to use ordinals or something like that. But if you ever find yourself doing 3 loops, maybe there's a justification for that. If you ever find yourself doing 4 nested loops, 5 nested loops, 6 nested loops, you are probably doing something wrong. Right? Rethink what you're doing. That's what we call a code smell. Right? So if something smells, like if you go to the refrigerator and you know that yogurt that's been sitting in there for 2 weeks, is it still good or not? Right? Are you going to taste it or are you going to smell it? And if there's a smell, there's probably something wrong. Right? There's no need to investigate further by eating it. You throw it away. Yeah, the code smells are exactly the same. It's not necessarily wrong, it's not necessarily bad, but there's something fishy about it. There's something smelly about it. Right? And so code smells are a good indication that you're probably doing something wrong. Linters can find a lot of those things. But other patterns that are perfectly valid are probably code smells. They're probably telling you there's probably a better way of doing this. Rethink what you're doing. Rethink your design. Right? So let's take a look at an example of a nested for loop. I'll just go ahead and go with 2 loops here. For int I equals 0, I is less than, say, 10, we'll go 1. I less than or equal to 10 because this is familiar. I plus plus. Now inside this, I'm going to put another loop. For int, can I reuse I? I is an index variable for the outer for loop. Can I use the same variable for the inner for loop? Nope. You can't redefine it, but also it's not a good idea to do so because now I've got 2 I's, right? and that's good in general if it's EYE, but it's not good if it's two variables, right? J, I'll start at, why did I go to J, by the way? I, J, and then what do you think I go for next? K if need be, L, M, N if you want to, but again, code smell, you probably don't want to go past 3 loops. J is equal to 1, J is less than or equal to 10, J plus plus. And I'll print both of these out. Print F I equals %D. I'll format it so that they're all line up here nicely. And J is equal to %2D, and then end the line, I and J. All right? So how many things are going to be printed out now? And in what order? 100 things. Why did you say 100 things? So outer loop runs starting at 1. The inner loop is going to run how many times? 10 times. Then the outer loop goes I to 2. How many times does the inner loop run? 10 times. 10 times 10 is going to be 100. And what is it going to look like? 1, 1, 1, 1, 1, 1, 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? All the way up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then I becomes 2. And then J, I wrote that as I, yeah? Yeah. Again, it looks, no, it doesn't look anybody up there anymore. But those are, the first one is I, and the second one is J, trust me. Then it goes to 2, and then J again runs 1 up to 10. Right? Over and over and over again. You can see that this is going to be very, very daunting if you get to larger, even moderately small numbers. What if I go to 1,000 to 1,000? How many iterations is this going to go? 1,000,000, right? So I'm not caught in an infinite loop here. I'm just caught in a very, very inefficient loop. Now it's only inefficient because it's actually printing something. If I didn't print anything, it would actually probably go pretty quick. In fact, the compiler would probably optimize this away. If I wanted to, I can stop this now, of course, kill it. And I'll show you that it'll actually go quite quickly here in total by doing something else. So what I'll do is I'll say that the total is equal to total plus I times J. Okay? Now we're probably going to have an overflow issue here. That's fine. But I'll print out whatever I actually do get. Printf total is equal to %D and the line total. And you'll see that this will actually go by fairly quickly, because 1,000,000 things is nothing to a computer. Oops. There. Doing 1,000,000 things is nothing to a computer, but doing 1,000,000 input outputs, that's a lot, right? Because input output is so inefficient. Keep this in mind when you do system-level programming. Should I be printing stuff out with the system-level programming? Probably not, right? The I/O input-output is the most expensive thing when you're writing a program. If you can just do all the calculations and then report one result at the end, you see how lightning fast it is.
So if we wanted a string at the end, could we just keep adding to the string?
When we get to strings, you'll find out that you're going to have to allocate a hell of a lot of memory to do it. Because if you just want to keep concatenating onto the end of a string, and you'll have, say, 139 million characters, right? That's 139 million bytes. That's 139 megs, right? Not that bad with modern computers, but still, it's going to slow down because now you're doing memory stuff. All right. But what if I go up to 100,000, 1,000,000, 1,000,000? There we go. So anybody watch old westerns? There's an old western called Once Upon a Time in the Old West, right? Sergio Leone, I believe. And they've got a character in there. Of course, it takes place in the 19th century. So he's positing that, wow, this land must thousands of dollars or thousands of dollars. And the other character says, yeah, they call them millions, right? So What, thousands of thousands was millions. What is millions of millions? Call them quadrillions, don't we? That's 1 quadrillion. So again, we're not going to get the correct answer because of overflow here, but is it efficient? 1 million things to a computer is nothing. But guess what? What did I say? Quadrillion things to a computer? That's something.
How long will this take, you think?
Good question. We'd have to time it out. So we can probably get a good estimate here by going, let's go, what was it before, 1 million? We had 1,000. 1,000. So let's go 100,000 and 100,000, because then that other one will be 100 times 100 more, so 10,000 times slower. So if we can time this, there we go. So time A dot out. All right, so 1/4 of a second times 10,000. How many seconds is that? 10,000, so 2,500 seconds, 2 hours, 2 minutes. Yeah, 41 minutes. That's my estimate. So not centuries. We'll look at stuff that takes centuries if you do it wrong. And then if you do it right, it'll take seconds later on in the semester.
Does this correlate with processor frequency at all?
It does. I mean, if I took it to took it off of Amazon Web Services or whatever this is, that's probably not Amazon because it's a Microsoft product. But if I took it off of their web servers and put it on my, like 2080 Ti or something, it's probably going to go quicker, but not orders of magnitude quicker.
What was the command you used? Time?
Time. Yep. Time, and then whatever command you want after that, and it'll tell you the real time. Right there, the 2.68 seconds passed. The user time, and then the system time. The system time was nothing at all, right? Because there are lots of processes going on at the same time here. I don't know. Is H top on here? Nope. Top. Probably. There. There are all of the processes that are running right now, and then you see them going in and out of context. I don't know how many virtual processors we have here. One running. Looks like we only have a single CPU. Yeah. The Holland Computing Center, right? All right. So nested loops. Not generally a good idea, especially if you've got larger numbers like this, right? Because now everything compounds. 10 times 10 is 100. 100 times 100 is going to be 10,000. 1,000,000 times 1,000,000 is going to be a quadrillion, right? It gets slower and slower and slower. But you can do as many as you want. Avoid 3 or more nested loops, though, because that's probably a code smell. More nested loops is likely a code smell. All right? Not necessarily bad, but probably stinks. Make your code fragrant. All right. I did look it up, and the term lint actually goes back, it originated in C, and it went back to very early days of C. There was a Unix utility called lint or something like that that would go through and do static analysis on C code. I couldn't find, it's probably legacy software and it's probably not out there anymore, but it's just been built into GCC and other compilers now. Unfortunately, lots of code smells are not necessarily lint that can be found out by a compiler. You have to have human eyes at that point. We're not to the point where computers can write each other yet. Okay. All right, so pitfalls. All right. So consider the following piece of code. Tell me, what do you think it's going to do? It's a while loop. So int I is equal to 0. While I is strictly less than 10, do what? Say what? Is it actually going to print anything? Let's find out. Let's go ahead and quit top there. GCC demo. Okay. I typed my markdown code instead of my actual C code there. There we go, sorry. If you want to see how the sausage is made, that's what I just did. Here's how I'm typing all the notes. It's all done in Markdown, which is another markup language, minimalistic, so that you can get nice looking formats like this very, very easily. If you're interested, Markdown, it's what all the notes are posted in. When it actually gets rendered on GitHub, it's in this nice formatting. But if you want to, you can look at the raw file and start learning some Markdown if you want. All right. So what is this code going to do when I actually compile it? Go. Nothing. Why? Nothing. Infinitely. Do nothing, do nothing, do nothing, do nothing. Kill it. Eagle eyes.
Oh.
All right. If you missed that, don't worry. Come on. CC, demo. What should I always be doing? Wall flag. And it tells me that the while doesn't do anything. You have a semicolon immediately after your while invoking a do nothing infinite loop. Okay? Syntactically, it's correct, but it's got some lint in it, right? It smells, it stinks, and it results in an infinite loop here. Using while all the time will allow you to not have to strain your eyes all the time. Okay. All right. So that's an infinite loop. Again, the above will always will result in an infinite loop. Always use the while flag. You can kill a program with Control C. Yeah.
Just a little update. The quadrillion took 3 seconds, 3.21 seconds.
Oh, it did?
On this machine, yeah.
Oh well, you've got a nice map. Is it Air? Or?
It's the Pro.
Okay.
I think it'd be at least 10 minutes.
Yeah, I mean, this is, I don't know what kind of processor they're running on the cloud or whatever here. But remember, it's probably a Docker instance on top of a virtual machine, on top of a virtual server. And so this entire stack, I'm sure that is nowhere near as efficient as this. I mean, I got rid of the code, but I could test it locally on my machine too, and it would probably be faster, but yeah. Kick it up to a billion and billion, and it'll be, you said it was 3 seconds. It'll end up being 100 times as slow, so it'll be about 5 minutes. Right? If you can, then tell us what the results are. That's my estimate, though, 5 minutes. Right. All right, so consider the following code. And again, use your eagle eyes to tell me what's wrong. There's no increment operator, so what happens? Print 0, 0, 0, 0, 0, 0, 0, 0 forever, right? You're not making progress towards your terminating condition. Make sure that you have all 3 or 4 of those aspects: an initialization, a continuation, an increment towards your termination condition, and the actual body. Number 3. No braces. Right? So when syntactically you don't need braces, but I've always been writing them. And it's a habit you should get into. No matter what, write the braces. Why? What happens in this case? I is 0, while I is less than or equal, less than 10, print 0. It only binds to the next executable statement without those curly brackets. The indentation cannot be relied on here, right? In fact, I wonder what happens. I'm quite sure that this won't even come up as a warning anymore. Oh, it does. Nice. While class does not get guard. You indented it, but you probably didn't mean to do that, right? Wow, that's good job, GCC. Right? Very, very nice that you were able to detect that. Right? Usually they don't detect. They can't detect stuff like that. So what's the fix? Always write your curly brackets, whether you need to or not. That's best practice. Maybe one more. But for that, you're going to need a little bit of a history lesson. All right. Does anybody know what a zune is? All right. Did you ever own one?
Yeah.
This was within your lifetimes here. Come on. This is only 14 years ago, so you could have owned one as a, I don't know, a 4-year-old or something. So did you own one?
My older brother had one.
Okay, there we go. All right. Zune. It's a Microsoft product. There it is. It was cool. Well, it's an iPod. It's an iPod knockoff, right? It played music and video, right? And why was it a nice product? Because it was $100 cheaper than an iPod. Physical stations by forwarding and stuff like that. But it was a pretty cool product at the time because of its cheapness, right? And it didn't force you into the Apple ecosystem. I have no problem with the Apple ecosystem nowadays, or the Microsoft, I don't care. But anyway, on December 31st, 2008, every Zune, mine included, right, froze for 24 hours. And just as magically, 24 hours later, they all kicked back on. Right? Does anybody know why? So 2008 was a leap year. Right? So the following code was in a Zune subsystem. All right? So I'll go ahead and cut and paste this. And let's walk through it. So, say what? Oh, I don't know, 06, 07, I don't know. Yeah, before this, yeah. They were running fine for a year or two or whatever, right? But on December 31st, that was because it was a leap year, it was the 366th day. So days is strictly greater than 366, and we end up going into this while loop. Right? Is leap year is true because 2008, the year, was a leap year. So we end up going into this block right here. Is days, which was 366, strictly greater than 366? No. So this is false, and we end up doing nothing. Go back up to the top. Did we change days? Nope. So 366 is still greater than 365, and we come down here and execute all that again. It's still a leap year. Days is still is not strictly greater than 366, and so we get caught in this infinite loop, but only for 24 hours. Why? 367. At which point this does evaluate to true. It subtracts off 366 to get us back to day 1, and now it is 2009. So, what's the problem?
You were in an infinite loop
For 1 day. What's the fix, I should say then? Greater than or equal to right here, right? Now, why did this get overlooked? I mean, it's not a fatal error. I mean, so what? You can't listen to your music for 24 hours, right? But think about this being in this kind of bug being in a medical application that says how much insulin to give somebody, or it's on a $60 million Mars probe that tells you when you should be hitting those thrusters to land properly, right? And those are two bugs that have happened before. There have been bugs that have killed people because of misdosing. There have been bugs that have destroyed 2 Mars probes. Not necessarily this way, but one of the Mars probes many years ago, like in the 90s, failed because it was converting. One system thought it was metric, and another system thought that it was imperial. So instead of going 100 miles an hour, or 100 kilometers an hour, it thought it was going 100 miles an hour, and instead of landing properly, it just crash landed right into Mars, right into the Mars surface. Now, if there had been people aboard, right, simple testing would have told you all of this. What did these folks fail to do? They failed to test a corner case. I'm sure that they just did some ad hoc testing. Yeah, the Zune works. It plays music. Great. Let's go. Right? Ship it. What did they not test? They didn't test the eventuality for a leap year. They didn't test whether or not, all right, well, what happens on the last day of a leap year? Let's go ahead and simulate that, see that it gets caught in an infinite loop, and oh, now we've got a problem. Those corner cases that you need to test, right? And if they weren't, since they were not doing proper testing, these are the kinds of things that happen. And when when it only costs you 24 hours on a second-tier product, nobody really cares. Microsoft's reputation goes down a little bit, maybe their stock goes down, and then 20 years later, it's more than recovered, right? So no big loss. But when you're talking about lives, when you're talking about irreplaceable $60 million Mars probes, right, that set back a space program by maybe a decade or so, right, then that stuff matters, right? So there are a whole bunch of checks and balances in place. This is why it's writing system critical stuff in certain aspects, and they have tons of regulations now. Writing just some random web app, though, doesn't require that level of testing unless there's millions of dollars at risk. Right? There's another bug a while ago that they automated trading, and I think it was, I forget what it was, but it triggered like the sell-off. Right? Take stock that's worth $100, and for this bug said, we need to sell it quickly for $5, right? And of course, everybody's going to pick up that kind of a sale, right? And so they sold off millions of dollars. That trading firm lost millions of dollars for their clients. Oh well. That's why there are lots of SEC regulations and electronic transfer regulations that dictate the amount of testing you should be doing on system critical stuff. All right, not that there's anything that you will experience in this course that is system critical. About the worst thing that can happen is we call it clobbering. You can clobber your own files. You can get it caught in an infinite loop and then have to kill it. At very worst, you can close your browser and start over, right? So don't worry about it. Play with things, break things intentionally. See if you can break them. Do be careful though. Okay, so I've got this nice demo file. You might have seen, and be careful with what websites you're looking at, not because of cheating, but because there's so many junk websites out there that tell you how to do things in C that are completely wrong. Even some of the top answers in Stack Overflow are completely wrong in their answers. So take all of that stuff with a grain of salt. Let me go ahead and show you what happens when I try to do something like this. Demo.c, or actually, out. Demo.c, demo.c. Right? So let me highlight this so that you can actually see it. Has anybody seen the O flag? I've tried to cut it out of my curriculum entirely. If I still have it in my handouts, let me know. So yeah, what does the O flag do?
For the output file, you can either have it be the file path or the name that you want the output.
Exactly. So by default, it's a.out, right? And that's what I encourage you to use. If I want b.out, right? It'll produce a file. See that? b.a.out, right? And because I mistyped there, but it'll output this file instead. Be careful, because what if you do something like this? Demo.c. Right? Now again, let me highlight this. Output the executable to a file called demo.c after you've compiled the file demo.c. Oh, wow. Very good job, GCC. Usually it will not let, it's not letting me do this because it's going to the same output file here. It's protected me from myself. Thank you. All right. Not every configuration will be this sophisticated and this smart. What would happen if it didn't prevent me from doing this? Goodbye file. Right? It would have all been clobbered, is what we call it. When you overwrite a file, you are clobbering a file. Right? Yeah.
Can you decompile something? Like if you
Good question. You can do that hex dump that we did before, hex dump of a.out. You can take that machine code and you can try to translate it back to the assembly code. That will work, but from assembly code to C, no. Because you can have two different programs that might compile to the same assembly code, right? And so it's not even reversible at all. Now, other languages like Java, you can decompile, but you do lose some things in the process. You can get as close as you can. I mean, I'm sure that there are tools out there that will get as close as possible to the original, but there's no guarantee on anything. Because ultimately, what the compiler is also optimizing things. So even if you write this for loop, it will say, the compiler says, okay, well, the efficient way of doing this is to do it a completely different way. It might even rewrite your code, right? And then, to an equivalent code, then compile to assembly. Things like preprocessor directives. Define, pi to be 3.14159, right? All instances of pi are gone before the compiler even touches it. Right? So you'll never recover the original 100%. Other questions? All right, we'll continue with this on Monday. Otherwise, this Friday, you've got your lab 3 and your hack 3, which are all in conditionals.